In the vast darkness between stars, objects drift. They tumble through the cosmic void with no allegiance to any sun, no orbital dance to define their path. These are the interstellar wanderers, chunks of rock, metal, and ice that was ejected from their birth systems millions or billions of years ago. They carry within their crystalline structures the chemical signatures of distant worlds, the frozen breath of alien atmospheres, the dust of stars that died before our sun was born. The galaxy teems with such nomads. Astronomers estimate that trillions of these rogue objects cross the space between stellar neighborhoods, some no larger than pebbles, others massive enough to dwarf mountains. They move in profound silence, unmarked by the warming touch of starlight, their surfaces sculpted only by the slow erosion of cosmic radiation and the occasional collision with interplanetary dust. Each carries its own microhistory, a record of the stellar nursery where it formed, the planetary collision that launched it into exile, the eons of cold journey through the galactic medium. Most of these wanderers will journey for eternity without ever encountering another world. They are cosmic hermits, destined to drift through the galactic suburbs until the universe grows cold and the last stars burn out. Their trajectories follow the gentle gravitational currents of dark matter, those invisible rivers that guide the galaxy's architecture. Some follow orbital paths around the galactic center that take them through spiral arms heavy with dust and newborn stars. Others ride the tidal streams left by ancient galactic collisions, cosmic highways that stretch across hundreds of light years. Yet some, a precious few, find themselves caught by the gravitational embrace of a passing star system. When this happens, they become temporary visitors, the hyperbolic trajectories carrying them briefly into the warmth of solar winds before flinging them back into the eternal night. The encounter transforms them. Solar radiation sublimes their surface ices, creating temporary atmospheres that glow in the darkness. Gravitational forces stress their internal structure, sometimes breaking them apart into families of fragments. For a few months or years, these ancient wanderers taste what it means to belong to a star. Our solar system, like all stellar neighborhoods, sits within streams of such material. The local standard of rest, the average motion of stars in our galactic region, carries the sun and its planets through clouds of interstellar dust and occasional larger debris. It is a slow, cosmic migration, our entire system moving at roughly 20 kilometers per second relative to the surrounding medium. This motion creates a cosmic headwind, a flow of interstellar material that the solar system encounters as it orbits the galactic center. The sun's heliosphere, that bubble of charged particles extending far beyond Pluto's orbit, acts as a filter for this incoming material. Small dust grains get deflected by magnetic fields, while larger objects punch through unimpeded. The heliopause, where solar wind meets interstellar medium, marks the boundary where truly alien matter first encounters our sun's influence. It is a region of complex physics, where particles accelerate and magnetic fields reconnect, creating aurora-like phenomena in the deep outer solar system. Yet here lies a quiet mystery that has puzzled astronomers for decades. If interstellar objects regularly enter our solar system, why have we only recently begun to detect them? The mathematics suggest that several should pass through each year, some large enough to observe with ground-based telescopes. Computer models of galactic dynamics predict a steady influx of rogue planets, asteroid-sized bodies, and comet-like objects. The numbers are compelling. Our stellar neighborhood should be rich with such visitors. Perhaps they arrive more frequently than we realize, masquerading as ordinary asteroids or comets until careful analysis reveals their exotic origins. Many may follow trajectories so similar to native solar system objects that they escape notice entirely. Others might fragment upon entering the inner solar system, their pieces scattering into meteoroid streams that pepper Earth's atmosphere for centuries afterward. The distinction between native and foreign becomes blurred across astronomical timescales. The detection challenge compounds the mystery. Ground-based telescopes scan for objects with unusual orbital characteristics, trajectories too energetic to be bound by solar gravity, compositions that don't match known asteroid or comet families. But such surveys are recent innovations, their databases spanning mere decades against billions of years of cosmic history. They're archaeological tools attempting to reconstruct an ancient story from contemporary fragments. The implications ripple backward through geological time. If such visitors arrive today, they have been arriving for billions of years, an unbroken procession of cosmic messengers carrying the chemistry of distant stars to Earth's doorstep. Only took 4.5 billion years for us to notice them properly. Some carried ice older than our oceans, preserving water molecules that condensed in the outskirts of alien solar systems. Others bore metals forged in supernovae that preceded our sun's birth, their atomic nuclei carrying the electromagnetic fingerprints of stellar explosions. All of them, in their silent way, have been writing their signatures into Earth's history, one gentle collision at a time. They have peppered our planet's surface with exotic isotopes, seeded our atmosphere with cosmic dust, contributed trace elements to our oceans. Their influence operates on scales both vast and intimate, shaping the chemical evolution of worlds while depositing individual atoms into growing crystals. The very ground beneath our feet contains their ancient gifts, scattered and mixed with terrestrial matter until the distinction dissolves into geological deep time. 4.5 billion years ago, Earth spins beneath a sky that knows no mercy. The late heavy bombardment reaches its violent crescendo, transforming the young planet's surface into a molten wasteland of impact craters and lava seas. Yet, within this chaos, a more subtle story unfolds. One written not only by the familiar debris of our own solar system, but by ancient wanderers that have travelled between the stars to find their way here. The bombardment represents the final stage of planetary accretion, a cosmic house-cleaning as Jupiter's gravity stirs the asteroid belt and sends rocky fragments careening through the inner solar system. Most of these projectiles are natives, chunks of material left over from the solar nebula's collapse, bearing the chemical signatures of our sun's stellar nursery. They carry within their crystalline matrices the isotopic ratios that define our cosmic neighbourhood, the trace elements that condensed from the same primordial cloud that birthed the planet. But scattered among this native debris, rarer visitors make their presence known: interstellar objects, ejected from distant star systems during their own epochs of planetary formation, drift through the galactic medium until our sun's gravity captures them in hyperbolic embrace. These cosmic refugees arrive bearing alien chemistry, isotopic ratios that don't quite match solar system norms, trace elements forged in different stellar furnaces, organic compounds assembled under foreign skies. The distinction matters more than early Earth might realize. While native asteroids deliver familiar materials, iron from the solar nebula's metal-rich inner regions, water ice from the cooler outer zones, interstellar visitors carry chemical diversity that speaks of other worlds. Some bear the signatures of red dwarf star systems, where planetary formation occurred under dimmer, redder light. Others originate from massive stellar systems that burned bright and fast, enriching their surroundings with heavy elements before exploding as supernovae. During these bombardment epochs, Earth's surface remains largely molten, Impact energies exceed the threshold for global magma oceans, creating a world where solid crust forms only to be remelted by the next cosmic collision. Yet even in this hellish environment, the planet begins to differentiate between native and foreign contributions. Interstellar materials, arriving with hyperbolic velocities often exceeding 20 kilometers per second, penetrate deeper into the impact-generated magma than their slower-moving native counterparts. The physics of high-velocity impact creates unique conditions for preserving alien chemistry. When interstellar objects strike at cosmic speeds, they generate pressures exceeding 1 million atmospheres and temperatures rivaling stellar cores. These extreme conditions forge new mineral phases, structures that can only form under the precise combination of pressure, temperature, and chemical composition present during hypervelocity impact. Some of these phases incorporate interstellar trace elements in ways that terrestrial geology cannot replicate. Deep within the impact melt sheets, exotic isotopes begin their slow integration into Earth's growing chemical inventory. Stellar nucleosynthesis in distant galaxies has produced subtly different ratios of common elements. Silicon with unusual isotopic signatures, iron bearing the fingerprints of different supernova types, carbon that condensed in the atmospheres of alien red giants. These variations are minute, detectable only with the most sensitive modern instruments. Yet they represent genuine alien additions to Earth's composition. The bombardment's timing proves crucial for preserving these interstellar contributions. During the Hadean Eon, Earth's magnetic field remains weak and variable, offering little protection from cosmic radiation. Solar wind particles strip away much of the early atmosphere, carrying terrestrial molecules into space while simultaneously depositing interstellar dust swept up by the sun's motion through the galaxy. This creates a complex exchange where Earth loses native material while gaining foreign atoms, a cosmic metabolism that operates on geological timescales. Gravitational dynamics complicate the story further. Not every interstellar visitor arrives as a direct impact. Some enter highly elliptical orbits around the Sun, their trajectories gradually decaying through gravitational perturbations from the giant planets. These temporary captives may orbit for millions of years before finally encountering Earth, their surfaces slowly altered by solar radiation and thermal cycling. By the time they impact, they carry both their original interstellar chemistry and new compounds formed during their residence in our solar system. The largest interstellar impactors create basins comparable to those carved by native asteroids. The South Pole Aitken Basin on the Moon, formed during this epoch, may preserve within its central peak rings the shocked remnants of an interstellar object that wandered for eons before finding its way to our neighborhood. Such impacts excavate material from hundreds of kilometers depth, mixing interstellar chemistry with native rock in proportions that will influence planetary evolution for billions of years to come. Yet most interstellar contributions arrive more gently. Smaller objects fragment in Earth's thin early atmosphere, creating meteor showers that deposit their exotic chemistry across vast areas. These cosmic dustfalls lack the drama of major impacts but provide more uniform distribution of alien materials. They settle into the growing sedimentary record, becoming part of the chemical foundation upon which later geological processes will build. The bombardment's interstellar component remains largely invisible to casual observation. Alien chemistry gets thoroughly mixed with native materials during impact processing, creating hybrid compositions that require sophisticated analysis to decode. Only the most subtle signatures survive, slight variations in isotopic ratios, trace elements present in unusual combinations, mineral phases that hint at formation under non-terrestrial conditions. These whispers of distant worlds become permanently embedded in Earth's geological record. As the late heavy bombardment gradually subsides, Earth inherits a surface enriched by contributions from across the local galactic neighborhood. The exact proportion remains uncertain. Perhaps one impact in 10,000 carried interstellar origins, or perhaps one in a million. The mathematics of detection and the chemistry of preservation make precise accounting impossible across such vast timescales. Yet the principle stands. From its earliest moments, Earth has been shaped not only by local materials, but by cosmic wanderers carrying the chemistry of distant stars. The young planet settles into a more peaceful existence as the bombardment wanes, its surface finally cool enough to support stable oceans and the first tentative experiments in chemical complexity. But the interstellar additions continue, now at gentler rates that allow their exotic chemistry to be preserved and studied. Only took a few 100 million years to clean up the neighborhood properly. Some visitors brought water from stellar nurseries older than our sun. Others delivered organic compounds assembled in the cold depths of interstellar space. All contributed to the growing chemical diversity that would, in time, provide raw materials for life's emergence. The chemistry of worlds begins with starlight and ends with stone. But between these extremes lies a universe of subtle transformation that interstellar objects carry across the cosmic void. Each wandering fragment bears within its crystalline matrix the atomic fingerprints of its birth system, isotopic ratios that speak of different stellar furnaces, trace elements forged under alien conditions, molecular assemblies that condense from the breath of distant suns. When these cosmic messengers finally encounter Earth, they deliver chemical gifts that expand our planet's elemental vocabulary in ways both profound and whisper quiet. Consider the isotopic signatures that distinguish interstellar materials from their terrestrial counterparts. On Earth, the ratio of oxygen 16 to oxygen 18 reflects the specific conditions present in our solar nebula 4.5 billion years ago. Temperatures, pressures, and chemical gradients that were unique to our Sun's formation process. But interstellar objects carry oxygen isotopes with subtly different ratios, forged in stellar environments where nuclear burning proceeded under different conditions. Red dwarf systems, with their cooler hydrogen fusion, produce oxygen with distinct isotopic fingerprints. Massive stars that burn helium in their cores create yet another signature, one that gets distributed through space when they explode as supernovae. These differences are minute, often less than 1 part per thousand, yet they represent genuine alien additions to Earth's growing chemical inventory. Modern mass spectrometers can detect such variations in meteorites and deep crustal rocks, revealing traces of interstellar contribution that have survived billions of years of geological processing. The signatures are strongest in materials that formed during Earth's earliest epochs, when interstellar bombardment rates were highest and planetary differentiation had not yet homogenized the alien chemistry throughout the mantle. Water molecules present perhaps the most compelling case for interstellar chemical influence. Ice forms readily in the cold depths of space, condensing onto dust grains in molecular clouds and the outer regions of stellar systems. Different formation environments produce ice with characteristic chemical signatures, not just isotopic variations in hydrogen and oxygen, but trace impurities that reflect local conditions. Interstellar ice often incorporates methanol, formaldehyde, and other simple organic molecules that form through gas phase chemistry in molecular clouds. When heated during atmospheric entry or impact, these compounds decompose into smaller fragments that integrate into terrestrial chemical cycles. The deuterium content of water provides particularly clear evidence for interstellar contributions. Heavy water containing deuterium instead of ordinary hydrogen forms preferentially in cold environments where molecular motion is sluggish. Interstellar space with temperatures near absolute zero creates ideal conditions for deuterium enrichment in ice mantles coating dust grains. Earth's oceans show deuterium ratios that suggest multiple water sources, some matching the isotopic signature of native solar system materials, others pointing toward interstellar origins. Organic chemistry represents another frontier where interstellar objects have quietly influenced Earth's molecular landscape. The interstellar medium contains over 200 identified molecular species, including complex organic compounds like glycine, formamide, and polycyclic aromatic hydrocarbons. These molecules form through gas phase chemistry in molecular clouds, where temperatures are too cold for thermal decomposition but energetic enough for slow chemical reactions driven by cosmic radiation and stellar ultraviolet light. When interstellar objects carry these preformed organics to Earth, they deliver chemical complexity that terrestrial processes would require millions of years to synthesize from simpler precursors. Some of these compounds possess chirality, handedness that determines how they interact with biological systems. Interstellar chemistry appears to show slight preferences for certain chiral forms, potentially biasing Earth's early molecular inventory toward the configurations that life would eventually adopt. The role of catalytic metals in this process deserves particular attention. Stellar nuclear synthesis in different types of stars produces varying abundances of transition metals like iron, nickel, cobalt, and the platinum group elements. These metals serve as catalysts for organic chemistry, facilitating reactions that would otherwise proceed too slowly to be geologically relevant. Interstellar objects from metal-rich stellar environments deliver higher concentrations of these catalytic species than typical solar system materials, potentially accelerating the development of complex chemistry in Earth's early oceans. Phosphorus presents a particularly intriguing case study. This element, essential for biological molecules like DNA and ATP, occurs in relatively low abundance throughout the universe. Most stellar environments produce phosphorus primarily through supernova nuclear synthesis, creating spatial variations in phosphorus availability across different regions of the galaxy. Interstellar objects originating from phosphorus-rich stellar neighborhoods could have delivered concentrated sources of this crucial element to Earth's early chemical inventory. The preservation of interstellar chemical signatures through geological time requires specific conditions. High-temperature processes like metamorphism and magma differentiation tend to homogenize isotopic ratios and decompose complex organic molecules. Only materials that avoid extensive thermal processing retain clear evidence of their cosmic origins. This includes certain classes of meteorites, deep crustal rocks that have remained geologically quiet, and sedimentary deposits that formed under low-temperature conditions. Some of the most compelling evidence comes from studying ancient sedimentary rocks that formed during Earth's earliest epochs. Banded iron formations from the Archean Eon sometimes contain isotopic anomalies that point toward extraterrestrial sources. These anomalies are subtle, variations in sulfur isotope ratios that don't match typical terrestrial values, or trace element patterns that suggest input from sources with non-solar compositions. The challenge lies in distinguishing between interstellar and asteroidal contributions. Both deliver extraterrestrial materials to Earth's surface, but asteroids and comets from our own solar system carry chemistry that reflects local conditions during planetary formation. True interstellar objects bring chemistry from entirely different stellar environments, with isotopic signatures and trace element patterns that speak of alien star formation processes. Modern analytical techniques are only beginning to unravel these subtle distinctions, Advanced mass spectrometry can measure isotopic ratios to parts per million precision, revealing variations that were invisible to earlier generations of instruments. X-ray spectroscopy identifies trace elements present in concentrations too low for traditional chemical analysis. These tools are rewriting our understanding of how interstellar materials have influenced Earth's chemical evolution. The implications extend beyond mere chemical accounting. If interstellar objects have been delivering exotic chemistry to Earth for billions of years, then our planet's molecular inventory reflects not just local solar system processes, but also the broader galactic environment. We are, in a very real sense, composed partly of materials that condensed around distant stars and travelled through interstellar space to find their way here. The process continues today. Every year, Earth's atmosphere encounters thousands of tons of interplanetary dust, some fraction of which may have interstellar origins. These microscopic particles settle into ocean sediments and terrestrial soils, adding their atomic contributions to the ongoing chemical evolution of our planet. Only took us a few billion years to start paying attention to this cosmic chemistry lesson. Some particles carry iron forged in supernovae that exploded before our sun existed. Others bear carbon that crystallized in the atmospheres of ancient red giants. All contribute to the vast slow-motion experiment in planetary chemistry that has been running since Earth's formation. 4 billion years ago, the Hadean Eon draws toward its close, and Earth exists as a world caught between fire and ice. The planet's surface has finally begun to solidify into something approaching permanent crust, though volcanic activity continues to reshape vast regions with each passing millennium. Above this restless landscape, the sky tells a different story, one of gravitational capture and celestial mechanics playing out on scales that dwarf terrestrial concerns. The young solar system's gravitational architecture remains unsettled, its outer planets still migrating through orbital resonances that send cascades of debris spiraling inward toward the Sun. Within this dynamic environment, interstellar objects find their way into temporary residence, unlike the brief flyby encounters that characterize modern visits. The Hadean solar system possesses the gravitational complexity necessary for genuine capture. Jupiter and Saturn, still massive enough to perturb incoming trajectories but not yet settled into their current orbital configurations, create zones of unstable equilibrium where interstellar wanderers can be temporarily snared. These captured objects follow highly elliptical orbits that may persist for millions of years before planetary perturbations either eject them back to interstellar space or send them crashing into the inner planets. The physics of gravitational capture during this epoch creates unique opportunities for chemical exchange. An interstellar object entering the outer solar system encounters not just the Sun's gravity, but also the complex gravitational environment created by migrating giant planets. Three-body interactions between the visitor, the Sun, and a passing planet can drain orbital energy, converting a hyperbolic escape trajectory into a bound elliptical orbit. The mathematics are elegant. What begins as a brief encounter becomes a prolonged gravitational dance that may last for geological ages. During these extended captures, interstellar objects undergo gradual transformation. Solar radiation sublimates their surface ices, creating temporary atmospheres that interact with the solar wind and planetary magnetospheres. Cosmic radiation penetrates their interiors, altering molecular structures and creating new chemical compounds through radiolysis. Thermal cycling between perihelion and aphelion stresses their internal structure, sometimes leading to fragmentation events that scatter their exotic chemistry across multiple smaller bodies. The gravitational resonances that characterize the outer solar system during this period create preferred capture zones where interstellar objects accumulate. These regions, analogous to modern asteroid belts but far more dynamically active, serve as temporary repositories for alien chemistry. Objects trapped in these zones gradually have their orbits circularized through repeated gravitational encounters, transforming from obvious interstellar visitors into apparent natives of the solar system. Some captured visitors develop comet-like characteristics as they adapt to their new environment. Solar heating drives volatile compounds from their surfaces, creating the familiar coma and tail structures associated with comets. But their chemical composition tells a different story. Spectroscopic analysis of their outgassing reveals isotopic ratios and molecular species that don't quite match typical solar system values. They are cosmic immigrants, gradually assimilating into the local population while retaining subtle signatures of their foreign origins. The Hadean Earth benefits directly from this gravitational processing of interstellar materials. Objects in highly elliptical capture orbits occasionally pass close enough to Earth's growing gravitational sphere of influence to be further perturbed into collision trajectories. These impacts deliver not just the raw materials of interstellar objects, but also their accumulated modifications from extended residence in the solar system. The chemistry represents a hybrid of alien and local influences. Interstellar organics processed by solar radiation, alien ice mixed with solar system dust, trace elements that bear the isotopic signatures of distant stellar nucleosynthesis, but also the radiation damage accumulated during million-year orbits around our Sun. The timing proves crucial for Earth's chemical evolution. During the Hadean, the planet's surface temperature remains high enough to maintain global magma oceans periodically, but cool enough between major impacts to allow water vapor to condense into the first tentative oceans. This creates ideal conditions for preserving and concentrating the exotic chemistry delivered by captured interstellar objects. Unlike the violent impacts of the late heavy bombardment, which vaporized both projectile and target, gentler collisions during the late Hadean can preserve complex organic molecules and delicate isotopic signatures. The process of capture and collision operates on multiple scales simultaneously. Large interstellar objects, perhaps kilometers in diameter, undergo capture as single entities and may orbit for millions of years before impact. Smaller fragments, created when larger visitors break apart under tidal forces or thermal stress, scatter their debris throughout the inner solar system. Microscopic dust grains, liberated from sublimating surfaces, spiral inward under the Poynting-Robertson effect and rain down upon Earth's atmosphere as cosmic dust. Each scale of interaction contributes different aspects of interstellar chemistry to Earth's growing inventory. Large impacts deliver concentrated doses of alien materials, creating localized regions where interstellar isotopic signatures dominate over terrestrial values. Medium-sized impacts distribute exotic chemistry more broadly, mixing alien elements with native materials in proportions that will influence regional geology for billions of years. Dust influx provides continuous background addition of interstellar atoms, ensuring that even quiescent periods between major impacts see steady accumulation of cosmic chemistry. The gravitational dynamics of the Hadean solar system also create opportunities for multiple encounters between Earth and the same interstellar object. An initially captured visitor might pass close to Earth several times during its million-year orbital evolution, each encounter potentially delivering fragments to our planet's surface. This serial bombardment by related materials creates coherent chemical signatures that can be distinguished from the random impacts of unrelated objects. The preservation of these signatures in Hadean rocks presents enormous challenges for modern analysis. Most rocks from this epoch have been thoroughly recycled through subsequent geological processes, their original chemistry homogenized by billions of years of metamorphism and magma processing. Only the most ancient zircon crystals, preserved within younger rocks like messages in bottles, retain isotopic memories of Hadean chemistry. These microscopic time capsules sometimes reveal anomalous isotopic ratios that hint at exotic sources, perhaps the last surviving evidence of interstellar contributions to Earth's earliest chemical inventory. The magnetic field dynamics of the Hadean Earth add another layer of complexity to interstellar object interactions. During this epoch, Earth's magnetic field was likely much weaker and more variable than today's dipolar structure. This provided less protection from cosmic radiation, allowing high-energy particles to penetrate deeper into the atmosphere and reach the surface directly. Charged particles from the solar wind could interact more directly with both the planet's surface and any captured interstellar objects, driving chemistry that would be impossible under modern conditions. Some captured interstellar objects may have persisted long enough to witness Earth's transition from the Hadean to the Archean eon. These ancient witnesses would have observed the gradual cooling of the surface, the establishment of stable oceans, and perhaps even the first tentative emergence of life. Their own chemistry, gradually altered by billions of years of solar system residence, would eventually contribute to the chemical environment that supported life's earliest experiments in self-replication. The gravitational capture process gradually becomes less efficient as the solar system matures. Jupiter and Saturn settle into more stable orbits, reducing their ability to capture passing interstellar objects. The population of small bodies in the outer solar system decreases through collisional evolution and planetary ejection. The window for efficient capture of interstellar materials slowly closes, though it never completely shuts. Only took a few 100 million years for the solar system to organize itself properly. Some visitors arrived carrying water older than Earth's oceans. Others brought metals forged in stellar explosions that preceded the solar system's formation by billions of years. All contributed to the complex chemical mixture that would provide raw materials for life's eventual emergence. The legacy of Hadean interstellar capture extends far beyond simple chemical addition. These ancient visitors established precedents for the ongoing exchange between our solar system and the broader galactic environment. They demonstrated that Earth's chemical evolution has always been influenced by contributions from cosmic sources, that our planet's composition reflects not just local solar system processes, but also the broader stellar neighborhood's chemical diversity. In capturing and processing these interstellar wanderers, the young solar system began writing the first chapters of a story that continues today, the story of how local worlds participate in galactic chemical evolution, one cosmic visitor at a time. 3.5 billion years ago, Earth's surface has finally achieved something approaching stability. The Archean eon begins with oceans that stretch from horizon to horizon, their waters dark and rich with dissolved minerals leached from volcanic rocks. These early seas know no oxygen. That revolutionary gas remains locked away in compounds, waiting for life to discover the alchemy of photosynthesis. Above the waves, an atmosphere of methane and carbon dioxide creates greenhouse conditions that keep the young planet warm despite the sun's dimmer youth. Into this alien seascape, interstellar visitors continue their ancient delivery service, bringing gifts of water, carbon, and phosphorus from distant stellar neighborhoods. The chemistry of these early oceans reflects contributions from multiple cosmic sources. Native materials, weathered from basaltic crust and delivered by local asteroids, provide the foundational inventory of dissolved elements, but superimposed upon this terrestrial baseline are subtle signatures of interstellar addition, isotopic ratios that don't quite match solar system norms. Trace elements present in unexpected combinations, organic compounds with molecular structures that hint at formation under non-terrestrial conditions. Water itself tells the most compelling story of interstellar contribution. The deuterium content of Archean oceans, preserved in ancient sedimentary rocks, suggests multiple sources for Earth's water inventory. Some matches the isotopic signature expected from native solar system materials, water that condensed from the solar nebula and was delivered by local comets and asteroids. But a significant fraction shows deuterium enrichment consistent with interstellar origins, water that formed in the cold depths of molecular clouds and was carried to Earth by cosmic wanderers. The distinction matters because different water sources carry different chemical passengers. Interstellar ice forms in environments where temperatures approach absolute zero, creating ideal conditions for trapping volatile organic compounds that would decompose under warmer conditions. When these icy visitors enter Earth's atmosphere, sublimation releases not just water vapor but also methanol, formaldehyde, hydrogen cyanide, and more complex organic molecules that were incorporated into the ice matrix during its formation in interstellar space. These organic additions to the early oceans provide raw materials for prebiotic chemistry. Hydrogen cyanide polymerizes in alkaline conditions to form adenine, one of the nucleotide bases essential for RNA and DNA. Formaldehyde undergoes condensation reactions to produce sugars, including ribose, the backbone sugar of RNA. Methanol serves as a carbon source for more complex organic synthesis, particularly in the presence of metal catalysts delivered by the same interstellar objects. The metal content of interstellar visitors proves particularly significant for ocean chemistry during the Archean. Different stellar environments produce varying abundances of transition metals, and some interstellar objects carry concentrated sources of iron, nickel, cobalt, and molybdenum, elements that serve as cofactors for biological enzymes. The delivery of these metals in association with organic compounds creates localized chemical environments where complex biochemistry becomes thermodynamically favorable. Iron presents a special case during the Archean. Earth's early oceans contain enormous quantities of dissolved ferrous iron, weathered from basaltic rocks under the reducing conditions that prevailed before oxygen accumulation. This iron remains in solution until something causes it to precipitate, forming the banded iron formations that characterize Archean geology. Some of these precipitation events may have been triggered by interstellar visitors carrying oxidizing compounds or catalytic materials that altered local redox chemistry. The phosphorus delivered by interstellar objects addresses one of the most challenging problems in early biochemistry. Phosphorus is essential for life. It forms the backbone of DNA and RNA, provides energy storage in molecules like ATP, and stabilizes cell membranes through phospholipid chemistry. Yet phosphorus occurs in relatively low abundance throughout the universe, and most terrestrial phosphorus is locked up in insoluble mineral phases that don't readily dissolve in seawater. Interstellar objects from phosphorus-rich stellar environments can deliver concentrated sources of this crucial element in forms that are more readily available for biological chemistry. Some carry phosphide minerals that react with water to produce phosphine and phosphite, reduced forms of phosphorus that can be more easily incorporated into organic molecules. Others contain organic phosphorus compounds synthesized through interstellar chemistry, providing direct sources of biologically relevant phosphorus molecules. The nitrogen chemistry of early Earth also benefits from interstellar contributions. The Archean atmosphere contains significant amounts of nitrogen, but most exists as chemically inert N2 molecules that resist incorporation into organic compounds. Interstellar objects carry nitrogen in more reactive forms, ammonia trapped in ice. organic nitrogen compounds like hydrogen cyanide, and nitrate minerals formed through cosmic ray interactions in space. These nitrogen sources provide alternatives to the challenging process of biological nitrogen fixation, potentially supporting more complex biochemistry in the early oceans. The spatial distribution of interstellar impacts creates chemical heterogeneity in the Archean oceans. Unlike modern oceans, which are well mixed by thermohaline circulation and wind-driven currents, early seas may have been more stratified and chemically diverse. Impact sites become focal points for exotic chemistry, creating localized environments where interstellar materials concentrate and interact with terrestrial components under conditions that don't exist elsewhere on the planet. Some of these impact-generated chemical oases may have persisted for millions of years, maintained by hydrothermal circulation that concentrates dissolved materials and provides energy for chemical reactions. The combination of exotic chemistry from interstellar sources and energy from geological processes creates natural laboratories where complex organic chemistry can proceed at rates faster than background oceanic conditions would allow. The timing of interstellar arrivals during the Archean proves fortuitous for chemical evolution. Impact rates have decreased from their Hadean peaks but remain high enough to deliver significant quantities of exotic materials. The ocean chemistry has stabilized sufficiently to preserve complex organic molecules, but oxygen levels remain low enough to prevent oxidative destruction of delicate compounds. This creates a Goldilocks zone in chemical space where interstellar contributions can accumulate and interact without being immediately destroyed. The preservation of interstellar chemical signatures in Archean rocks requires specific depositional environments. Most organic compounds decompose rapidly under typical geological conditions, but some environments favor preservation. Anoxic sediments where bacterial decay proceeds slowly, evaporitic basins where high salinity inhibits biological activity, and deep ocean sediments where low temperatures slow chemical reactions. Modern analysis of Archean rocks reveals subtle but persistent evidence for interstellar chemical contributions. Carbon isotope ratios in ancient organic matter sometimes deviate from purely biological signatures, suggesting input from cosmic sources. Sulfur isotope patterns in pyrite and other sulfide minerals show mass-independent fractionation that points toward atmospheric chemistry driven by interstellar sulfur compounds. Trace element patterns in sedimentary rocks occasionally reveal anomalous concentrations of platinum group elements that suggest extraterrestrial sources. The cumulative effect of billions of years of interstellar chemistry delivery transforms the Archean oceans into cosmic chemical libraries. Each impact adds new molecular species to the collection, expanding the inventory of compounds available for prebiotic experimentation. Some additions prove immediately useful for emerging biological systems. Others remain chemically inert until later evolutionary innovations find ways to exploit them. Still others may have influenced biological evolution in subtle ways that become apparent only through comparative biochemistry across different domains of life. The chemical complexity achieved in Archean oceans through this ongoing interstellar delivery process sets the stage for life's emergence and early evolution. The exotic chemistry provides raw materials and catalysts that terrestrial processes alone might have required millions of additional years to synthesize. In this sense, life on Earth benefits from galactic chemical evolution. The slow enrichment of interstellar space with complex molecules synthesized in stellar atmospheres and molecular clouds only took 1 billion years for the oceans to become a proper chemistry laboratory. Some visitors delivered water that had been frozen for millions of years in interstellar space. Others brought carbon compounds that had never felt the warmth of a star. All contributed to the vast chemical experiment that was preparing Earth for its most significant innovation. the emergence of self-replicating systems that would eventually transform both planet and cosmos. The Archean seas, enriched by gifts from distant stars, begin to stir with the first tentative movements of life,